Hey everyone, we are looking at section 2.7, which is looking more at proofs. This time we are going to look at paragraph proofs and flowchart proofs, okay? The first kind of proof that we're going to talk about is a paragraph proof. So in the last lesson, we did two column proofs where we had a statement and a reason. With a paragraph proof, all we're going to do is we're going to take each line of that proof and we're going to make it a sentence. So everything that was in step 1 will become a sentence. Everything that's in step 2 will become a sentence. And we'll get an example of this in just a minute. Okay? The next is a flowchart proof, which ends up taking statements and reasons and it puts them in boxes and then draws arrows so that as you move through the proof, you see where each of the steps come from. And we'll look at an example of that in a little bit. So the first thing that we're going to look at is two of our theorems for today. Okay, the first one, or three theorems, I'm sorry. We're going to look at the common segment theorem, which simply says that if I know, and then I have a segment like this, okay, where it's broken into 3 pieces. If the outside 2 pieces are the same length, well, then that means that this segment here is going to be the same length as this segment here because I know BC is going to be congruent to itself. So let's just put some numbers in so that helps this make sense. And again, please, you don't need to write the numbers on your paper. I'm just going to put it in for explanation's sake. So if AB is 5, that's going to make CD 5, which would make BC, I don't know, we'll just call it 10. Okay. Again, I'm totally making these numbers up. They don't come from anywhere. But if I look at AC, AC is going to be 15. If I look at BD, BD is also 15. So those are the same because they're both 5 plus 10. All right. So hopefully that kind of clears that one up a little bit. Vertical angles theorem. Remember that our vertical angles are the X. Okay. When I have 2 lines intersect, I'm going to create vertical angles. So I have a set of vertical angles here. These are going to be congruent. And a set of vertical angles here, these are going to be congruent. So our vertical angles theorem is going to be a pretty popular one we're going to see all throughout the year. So this one is important that you do know and understand that our vertical angles are congruent. All right, the next one is that if we have 2 congruent angles and they're both supplementary, okay? So the angles are not only congruent, they are also supplementary. That means each angle has to be a right angle. So let's look at it this way. Okay, I have a straight angle. I'm going to cut it in half. Okay, I know that if this is 180, each of these are 90. So these are congruent, they're 90 degrees, and they are supplementary. Okay? Let's take a look at a proof of the vertical angles theorem. Okay, so what we're really doing here is we're going to start by coming up with a plan. Okay? So what we're going to do is we're going to show that if 1 and 3 are vertical angles, that their measures are equal. Okay. I want to get to showing that, all right, I'm going to have a linear pair here, which means they're supplementary, which means they're going to add to 180. Okay. Then I have a linear pair here, which means they're supplementary and they're going to add to 180. So I'm going to get both of those are going to add to 180. Okay. I'm going to substitute in, well, if they both add to 180, they're going to equal each other. So then I can say that 1 plus 2 is going to equal 2 plus 3. And then the final step will be subtracting the measure of angle 2 from both sides. So my final step will be the measure of angle 1 is equal to measure of angle 3 by subtraction. Okay, so again, this is just I can't spell and talk. This is going to be just a general idea of where we're going to go. This is not a proof. This is just a plan for, this is the general way that we're going to get from point A to point B. All right. If you turn your page over with your notes, this is the actual flowchart proof. Okay. So again, this is proving that the vertical angles theorems are true. So the nice thing here is about the vertical angles theorem is we get to skip all of these steps in future proofs. We can just say, hey, if 1 and 3 are vertical angles, they are congruent by the theorem. And we skip all this stuff that's here in the middle. All right. So let's take a look real quick. I'm going to take a pause real quick and I'm going to go grab the picture that was on the other page so we can use that to look at. So hold on real quick. Okay, I grabbed that picture over here just so that way I can kind of reference it as we are going through the flow proof of the vertical angles theorem. So what I want you to notice here is our statements are inside the boxes, our reasons are underneath. So if we look, we are given that angles 1 and 3 are vertical angles. We are trying to prove that the measure of angle 1 is equal to the measure of angle 3. All right, this comes from the last page right here, where we have our given and our proof statements right here. Okay, yours are repeated on your notes on the same page, so you have that right there to look at. Okay, so know that, again, just like the proof in yesterday's notes with 2.6, where the first one when we proved the theorem was a little wonky, a little more detailed, a little more complicated than things that I'm going to ask of you right now, this one is going to go the same way. Okay, let's take a look at the structure of this proof. I am told that angles 1 and 3 are vertical angles. What does that tell me? It tells me that 1 and 3 are formed by the intersection of lines. Okay, that's what the definition is. All right, so when lines intersect, I create vertical angles. This information gave me this information right here, which is why there's an arrow from this box to this box. Okay, now if I have 1 and 3 are formed by intersecting lines, that gives me 2 pieces of information. So the first one is that angles 1 and 2 are a linear pair. So I'm going with these two here are a linear pair. Okay, by the definition. Definition is always going to describe what they look like. All right, well, what does that mean about them? If they're a linear pair, I'm going to know that angles 1 and 2 are going to be supplementary. All right, that is my linear pair theorem. Okay, so what does them being supplementary tell me? It tells me that they're going to add to 180. That is the definition of supplementary. All right, so again, this tells me this. This tells me this. Okay, and then I'm going to use both of these to get to the next step. We'll pause on that for just a second. Okay, so does everybody see how the arrows are pointing to the parts that come next? Okay, what does this information tells me? This guides me to this next piece of information. So that's why there's an arrow there. Okay, the other thing that we talked about, remember in that plan for the proof, was also showing that angles 2 and 3 are a linear pair. So what's basically going to happen is this right side is going to mirror the left side, but instead of angles 1 and 2, we're going to be looking at angles 2 and 3. So it's going to be the same thing. Angle 2 and angle 3 are a linear pair by the definition of a linear pair. Okay, what does that tell me? It tells me that angles 2 and 3 are supplementary by the linear pair theorem. Well, what does it mean to be supplementary? It means that their measures are going to add to 180. So I'm going to have measure of angle 2 plus measure of angle 3 equals 180 degrees. Okay, now, because these are both adding to 180, okay, they add to equal 180, this adds to equal 180, both pieces of information are going to give me this next one. I'm taking this and setting them equal to each other because they're both equal to 180. All right, that is substitution. Transitive also kind of works here. But substitution is really better. All right, then from here, I can subtract the measure of angle 2 from both sides and get the measure of angle 1 is equal to the measure of angle 3, which is where my proof is trying to go. Again, this proof is a little more challenging than what I'm going to be asking you guys to do kind of on your own. But I just kind of want you to see how many steps we save with proving these theorems and proving the vertical angles theorem. Okay. And what a flow proof is really going to look like. Okay. Inside the boxes are the statements. Underneath the boxes are the reasons. Okay. Let's take a look at the common segments theorem, which was the one we said like, hey, this is going to be this piece here is going to be the same length as this piece here, right? That is what we're trying to prove. So again, when you're trying to prove a theorem, you can't actually use it, all right? But we're going to start with looking and seeing AB is equal to CD. All right, that is given information. We know that that is true. All right, BC is equal to BC. That is our reflexive step. Remember, guys, it is reflexive, not reflective. It is a X, not a T. All right. Now, what did I do here? I have AB equals CD, and then I have a BC on both sides. So all I did was I added BC to both sides. So this is the addition property. Okay, I took this and I just added BC to both sides. Now, look here, what do I have? I have AB plus BC equals AC. This plus this equals the whole thing. Same thing on the other side. This plus this equals the whole thing. We are adding segments to equal the whole piece, so that is our segment addition postulate. All right. Then I have AC is equal to BD. Well, what did I do? Look at what's here. Okay. I'm going to notice I have AB plus BC. I have AB plus BC. So what I'm doing is I'm taking AC and I'm plugging it in for here. All right. Then I have the same thing over here. I have BC plus CD, BC plus CD. So I'm going to take this and I'm going to plug it in for this. So all I'm doing is I'm just substituting. All right. Any questions on that? Make a note somewhere and we will talk about it in class. All right. So now what we're going to do is we are going to take the proof that we just did, that 2-column proof, this one here, and we are going to write it as a paragraph proof. So the first line is AB is equal to CD, and our reason is given. So I'm literally going to write, it is given that AB is equal to CD. Okay, so line 1, sentence 1. If we go back, our next step is BC is equal to BC by reflexive. So then I can say the reflexive property shows that BC is equal to BC. Okay, the next thing we did was we added BC to both sides of this. So I can say AB plus BC is equal to BC plus CD by the addition property. Okay, then I can say using the segment addition postulate, I have that AB plus BC equals AC and BC plus CD equals BD. I like to wrap up the last sentence with a therefore. We can say, therefore, AC equals BD by substitution. Now, know that there's a lot of different ways to say this. Like, you can say that BC is equal to BC using the reflexive property or by the reflexive property, or basically the content of each sentence should remain the same. Like, you should have this information and the word given somewhere in that sentence. All right, you should have the reflexive property somewhere and this information. As long as the same information is in each sentence, the way you say it doesn't really matter. Okay, just make sure it makes sense grammatically. All right, but so all we did is over here, I have 5 steps. Over here, I have 5 sentences. So each sentence gets its own line. Okay, that's all, or each line gets its own sentence. That's all a paragraph proof is taking that and writing it out as a paragraph rather than in 2 columns. All right, let's look at another flow proof. Okay, so with this one, we are actually given the 2-column proof. Okay, I want to show you how we're going to take this and we're going to put it into a flow proof. So first off, I kind of want to make sure we understand it. So we have B as the midpoint of AC. All right, so what does that mean? If B is the midpoint, we know that those pieces are congruent, which means that their measures are equal. Okay, so definition of midpoint tells us that they're congruent. Definition of congruent tells that those measures are equal. Well, with our segment addition postulate, I can say AB plus BC equals the whole thing. So I'm just adding the pieces up. So now, because AB is equal to BC, I'm going to take AB and I'm going to plug it into BC so that I get AB plus AB equals AC by substitution. So I'm just plugging AB in here. And then I'm going to combine like terms. So we can say simplify or combine like terms. Either one of those is absolutely fine. Okay. So on your notes, you're able to look at this kind of at the same way. But let's take a look here. One thing I want you to notice that this proof here kind of flows horizontally, whereas our proof over here, too far, was more vertical. Okay, this went vertically because it was really long. It wouldn't fit on your page horizontally. Okay, this one will fit horizontally, so it's fine. All right, when you're creating your own flow proofs tonight, it doesn't matter which way you do it. Do you want to do everything vertically? Great, that's fine. Do you want to do it horizontally? Great, that's fine. Try just not to mix and match the directions that you're going in the middle. Okay, like if you need to go off to the side, like for one problem or one box, that's fine. But you kind of want to make sure everything flows really nicely and you're not searching for where your arrows are pointed to. Okay, when we check tomorrow, the important thing is going to be checking your arrows. All right, because each piece is going to lead to the next, and that's where our arrows are going to come into play. Okay, so it's what your arrows are pointing to that's important. So the first thing we're going to do is write our given information. All right, we have B as the midpoint. Of AC. Again, that information is given to us. Well, what did we get out of that? If you look at step 2, this tells us that AB is congruent to BC. That is my definition of a midpoint. Again, you're making sure that I see the word midpoint here. This is the definition I'm using, not bisect, because it doesn't say bisect here. It says midpoint. Okay? If AB and BC are congruent, what does that tell us? It tells that their measures are equal. So AB is equal to BC. All right? So that is our definition of congruence. Now, this by itself doesn't take me anywhere else. So this is where we're going to bring in that segment addition postulate from step 4 in your proof above on your notes. So we have AB plus BC equals AC. And that again is our segment addition postulate. Now, I don't get that from any of those other steps. Segment addition postulate always works and can always be put in, but it will be in its own line because this doesn't tell me segment addition. All right, this doesn't and this doesn't. Segment addition is its own standalone, so it gets its own line. Now, I use both of these steps together to do my substitution to get that AB plus AB is equal to AC. So again, we substituted that in. And now this tells me that 2AB is equal to AC. And again, that is either combining like terms or we can say simplify. I will take either one. All right. So again, guys, proofs are hard. All right. I want you to be at the point where you understand the proof after you see it. And I want you to make sure that it does make sense after the fact. Okay? It is still going to be hard. I understand that. I promise I will take care of you. I just need you guys to breathe your way through this. Keep trying every homework problem. Don't forget, with tonight's homework, it is still every time you see a proof, you copy down the whole entire thing. All the flowchart proofs, all of the given statements, the proof statements, everything is what you're going to write down. Okay? And then this is what your homework for tonight is. It is at the top of your notes as well. All right? I hope you guys have a wonderful evening, and I will see you later.